All right, guys, this is question number 1 from the 2017 AB exam. And in this question, you're given a table that's got height in feet and the area in square feet. And you're told in part A to use a left Riemann sum with three intervals indicated by the data in the table to approximate the volume of the tank, indicate units of measure. Now, something just to point out to you, when you integrate area, you get volume. And using Riemann sums is like a substitute to integration. So the Riemann sum is like integrating. So that's why you're getting volume out, okay? And if you use a left Riemann sum, you've got a 2 by 50.3 plus a 3 by 14.4 plus a 5 by 6.5, and that gives you 176.3 cubic feet. Part B, does the approximation in part A overestimate or underestimate the volume of the tank? Explain your answer. Okay, so what I've done here is I've just kind of sketched a picture of what A of H looks like. See, like it goes down by a lot, and then it starts to go down kind of by less and less. So something like that. Okay, it's going to have an upward concave to it like that. And if you draw a left-handed rectangle there, well, like there's my base, my left-handed height, and then you finish it over. Obviously that rectangle, part of it is above the curve, so it's an overestimate, and the best way you can say that is A of H is strictly decreasing. It doesn't matter about the concavity. If you were to draw a picture and you had something strictly decreasing there, and I drew a left-handed, I'd still be an overestimate. So it's really not based on the concavity, it's based on whether the function is increasing or decreasing. Okay, part C, the area in square feet of the horizontal cross-section at the height is modeled by the function given by f of h equals that crazy looking thing. Based on this model, find the volume of the tank, indicate units of measure. Okay, so now instead of using the table to talk about the area in square feet, they're now saying, forget that, we're going to use f of h instead. So f of h is like a substitute for what's in the table. Okay, and again, if you want to go from area to volume, you have to integrate. And it says the tank is 10 feet tall. So I'm integrating from 0 to 10 of f of h dh. And that's what I get right there. That's just like plugging into your calculator. And I know the test isn't a calculator test anymore, but it's still probably a good idea to see if you can use your graphing calculator. All right. And then part D, this one's kind of hard. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 foot per minute. Using the model from part C, find the rate at which the volume is changing when the height of the water is 5 and indicate units of measure. Okay, so in the words, they told us that H was 5 and that the rate of change of the height was 0.26, and they asked us to find the rate of change of the volume. And we're supposed to use what we found in part C. We found volume in part C, okay? So I just wrote an equation that was like this, but with a V right there. Now, something to point out, this equation here needs to be able to be used for the volume at any height, which is why that guy's an H now. And then this can be whatever other variable you want. I chose T, but it really doesn't matter, okay? So, and then you derive. So 1 dV dt. And then here, when I derive this, I'm deriving an integration with a variable as the upper limit. You plug in the upper limit and multiply by the derivative of the upper limit, right? Doesn't h derive to 1 dH dt? Okay, and then from there, you just plug a 5 in, so dV dt evaluated at 5. Well, f of 5, again, you're just plugging a 5 into that f of h equation given in part C, and that's 6.516 foolishness, times you know that dH dt is 0.26, and that gives you your final answer of 1.694 feet cubed per minute.